In previous videos, we talked about how to get to Mars and some of the issues with getting to Mars. And so this time we're actually going to go through getting to Mars and then an idea of how we could actually get to Mars a little bit more efficiently, especially with larger things like people. So the first thing that we do is we escape from Earth. That's the first step. The second step is doing a Hohmann transfer from Earth to Mars, which is two parts. So the first one is we start off in a circular orbit around the sun, and then we get into an elliptical orbit that goes from the Earth to Mars. And then once we get to Mars, we circularize our orbit, and then we land on Mars. This configuration happens every 2 years. And so we can do this Hohmann transfer every 2 years. What are the delta V's involved? We've talked about this before, but let's review them. So to escape from Earth, there's 11,200 meters per second delta V that's required. To get from a circular orbit to an elliptical orbit at Earth takes 2,943 meters per second. To go from an elliptical to circular at Mars takes about 2,650 meters per second. And to land on Mars with some atmospheric assists and some assumptions takes about 1,250 meters per second. So the total delta V is about 18,000 meters per second. So we can determine how much fuel we need. We could do a super bad assumption, and we could use a single stage rocket to actually do this. So the first thing we do is we calculate an initial amount of fuel. Then we assume roughly like 1/10 of the mass of the fuel was added for infrastructure. So basically the size of the rocket and everything. And then we do the final calculation of the mass. We want to put 3,000 kilograms payload on Mars. Remember that this is a bad assumption because it's a single stage rocket, and no one would ever use a single stage rocket to actually get to Mars. But we're just going to do this just to see what happens. We assume 3,500 meters per second exhaust velocity, which is critical. So we start with the rocket equation, and we plug in a bunch of numbers. We get the initial wet mass of the rocket. The fuel is about 517,000 kilograms of fuel if we use a single stage rocket to do this. Then we approximate the infrastructure, which is 1/10 of the mass of the fuel. So that would be 51,000 kilograms. So then we add those together. We add the mass of the rocket plus the mass of the payload, and we redo these. The dry mass is now 3,000 plus 51,700, and then we put those into the rocket equation, and we get the total mass needed to get to Mars is 9,500,000 kilograms. That is just astronomically huge. No rocket has ever been built this big. So that just shows you how ridiculous a one-stage rocket would actually be. What we would do instead is have something like a 4-stage rocket. Stage 1 would get us somewhat out of the atmosphere and about 1/3 of the escape velocity. Stage 2 would give us an escape velocity, so it would escape Earth, and that would be basically 2/3 of the escape velocity, the delta V that it needed to do. Stage 3 would do the Hohmann transfers to Mars, and stage 4 would be landing on Mars. So the delta V needed for stage 1 is around 3,700 meters per second. The delta V for stage 2 is 7,400 meters per second. Delta V for stage 3 is 5,400 meters per second. Delta V for stage 4, we're calling 1,774 meters per second. So the mass of the fuel for this stage is about 419,000 kilograms. So that would make the mass of the stage around 24,000 kilograms. Stage 2, the mass of the fuel would be roughly 118,000 kilograms. So the mass of the stage would be around 3,900 kilograms. Mass of the fuel for stage 3 is around 16,600 kilograms, and the mass of that stage is around 1,500 kilograms. And for stage 4, with just a lander, the mass of the fuel is about 2,400 kilograms, with the mass of the stage being around 134 kilograms. But if we summarize everything, the total mass of the fuel is now only 556,000 kilograms, which is significantly smaller than our single stage rocket. We do 4 stages, we get a much, much, much smaller rocket. Mass of the structures is around 30,000 kilograms, and the mass that we're putting on Mars is around 3,000 kilograms. If we add all of that up, we get a total mass pretty darn close to about 600,000 kilograms. So then if we compare that to actual rockets that have put stuff on Mars, this is all just sort of like approximations and some math and stuff and back of the envelope calculations that we're doing. If you compare that to a Delta IV Heavy wet mass, that's around 733,000 kilograms. So we're actually not very far off because Delta IV Heavies have been used to launch stuff to Mars. And so, we're actually within the right ballpark here. So now let's talk about the problem with this. So the problem is that a 4-stage rocket really only gets us 3,000 kilograms to Mars. So what if we want to take more to Mars? Well, the Apollo capsules were 50,000 kilograms, and they only carried 3 astronauts for about 10 days to the moon and back. So if we wanted to go to Mars, just putting them on Mars requires an 8-month journey and 5 astronauts. That's about what we would need. If you put 3 astronauts in a very confined space for 8 months, things could get dicey. You probably have all seen some reality TV shows. People can't get along very well for very extended periods of confinement. And so you put 5 astronauts instead in a little bit of a larger space, and you increase your probability of success dramatically. So a low estimate for the infrastructure would be about 100,000 kilograms. So 100,000 kilograms is a lot to actually get to Mars. We've talked about 3,000 kilograms. 100,000 is a lot more. So the Falcon Heavy, which is one of the biggest rockets available, couldn't even get that much to low Earth orbit. So then what do? Well, we have to do all of these things in stages. We have to basically build things in space. We need to come up with a completely different way of doing things. So the classic way, the way that we've talked about, is basically you escape Earth, you have a home and transfer to Mars, and then you land on Mars. You have stage 1, partially escaping Earth, stage 2, completing the escape from Earth, stage 3, doing the home and transfer, and stage 4, landing. So let's come up with an alternative idea. Basically, you could launch something, you could transfer to a different rocket, you do the home and transfer using what's called a long hauler, and then you transfer to a different rocket at the other end, and then you land on Mars. So let's refine this a little bit. So let's say that you launch to Leo and you put in astronauts or whatever type of supplies in Leo. Just like you did with the International Space Station, you launch stuff to Leo. You could build stuff in Leo, but we're not going to build stuff in Leo. We're just going to launch it to Leo. Then we're going to take stuff up to the L1 point with the Earth-Moon system, because that's sort of a gravitational null between the Earth and the Moon, and you're mostly escaped from Earth at that point. And so it's a good place to actually assemble stuff, and then you can launch from there. And you could use tugs, basically ships that are just fuel, and push them from low Earth orbit up to the Earth-Moon L1 point. Then, once you've built everything, you can take that and you can then use a long hauler, or take that long hauler that you assembled and then go to Mars. And then you stop at the Mars-Sun L1 point, and then you could use a Mars lander to go from the Mars-Sun L1 point to Mars and land on Mars. So we're going to use the Falcon Heavy as our main lifter. Getting stuff off of the Earth is hard, and so we're going to use technology that we've already built to do this. The Falcon Heavy can lift about 60,000 kilograms to low Earth orbit. We use the Falcon Heavy all the time now. Bigger rockets are on the horizon, so the problem becomes easier, but we're not going to use those bigger rockets. We're just going to use the Falcon Heavy. Now here's the big leap of faith. All right. We're going to assume that we have access to these Nerva tugs. Nerva is the nuclear rocket engines. And that is basically you have an engine and then you have a storage tank. So if you assume that the Nerva engine plus the tank itself is 20,000 kilograms, and then the exhaust velocity of the Nerva engine, the reason why we're using it, is 8,000 meters per second. 8,000 meters per second is about twice as high as any of the best chemical rocket engines available today. And so that is why we're using it, because it's much, much better. They're not developed now, but they are probably in development at this time. So the long hauler is going to be 100,000 kilograms without a tug, without a lander, or without fuel. We're going to say we're going to build our 5 astronauts a 100,000 kilogram structure that they can use to live on for 8 months. The lander on Mars is about 15,000 kilograms, which is about the same size as a Dragon capsule that takes the astronauts up to the International Space Station. So this is a pretty okay approximation also. And the delta V from the Sun-Mars L1 to service is around 2,500 meters per second, which is roughly half the escape velocity. And so we're using some atmospheric braking and stuff like that. So let's refine our ideas in more detail. So we're going to use the Falcon Heavy to put some big things into low Earth orbit. That's step 1. We're going to use our Nerva tug to take those heavy things from low Earth orbit to this Earth-Moon L1 point. Then we're going to assemble the Earth-Mars transport ship at the Earth-Moon L1 point. We're going to fuel that ship at the Earth-Moon L1 point. Then we're going to use the Nerva tug to take this transport ship, this long hauler, from the Earth-Moon L1 point to the Mars-Sun L1 point using a Hohmann transfer. Step 5 is we're going to undock the lander from the transport ship, and then we're going to land on Mars. So we have our Falcon Heavies that go up to low Earth orbit. We have our tugs that go up to Earth-Moon, and then we assemble stuff at Earth-Moon L1. We go from Earth-Moon L1 to Mars-Sun L1, and then we take our lander and we land on Mars. If we want to figure out how much fuel we need to actually do all of this, we need to work the problem actually backwards. Landing on Mars, the lander is going to be 15,000 kilograms. The delta V that we need is around 2,500 meters per second. We assume some sort of exhaust velocity of about 3,500 meters per second. And then the total wet mass is around 31,000 kilograms. So then we can go backwards and we can work the Mars-Earth L1 to the Mars-Sun L1 point using a Hohmann transfer, so that we know that the lander plus the fuel is 31,000 kilograms. We just did that math. We know our long-haul transporter is 100,000 kilograms. Our Nerva tug is 20,000 kilograms. So we add all of that up, and that's our dry mass. So that's 151,000 kilograms. So how much fuel do we need for that? We use the rocket equation. We need a delta V of 5,400 meters per second. And then we assume an exhaust velocity of our Nerva tug is 8,000 meters per second. And so the total wet mass is around 300,000 kilograms. Of that, 149,000 kilograms is fuel. This is actually a very small amount of fuel because we're using the Nerva engine, because the delta V is actually significantly smaller than the exhaust velocity. And that allows us to have such a small amount of fuel. Only 149,000 kilograms of fuel for this step. If we use normal chemical engines, it would be a lot more fuel than this. Now to assemble at the Earth-Moon L1, what are we going to actually do? So our lander and fuel is 31,000 kilograms. Our Nerva tug is 20,000 kilograms. Our long-haul transporter is 100,000 kilograms. The fuel is 149,000 kilograms. and the Falcon Heavy launches to Leo, you can only lift 60,000 kilograms at one time. The tugs from Leo to the moon, Earth L1, to get there requires a delta V of about 3,900 meters per second. So if we want to take the tug from Leo to L1, the Nerva tug is about 20,000 kilograms. Delta V is 3,900 kilograms. The exhaust velocity of the tug is around 8,000 meters per second. And so the total wet mass, using the rocket equation, is around 33,000 kilograms to take the Nerva tug out to L1. So the fuel is around 13,000 kilograms. So why did we just do this equation? Why did we do this calculation? Well, once we take something out to L1, then we need to get our Nerva tug back to Leo because we want to reuse it. We don't want to just launch the Nerva tug out to L1 and leave it there. We want to have it come back to Leo, refuel, resupply everything, and then take it back up to the moon, drop everything off, come back to Leo, etc., over and over and over again. And so in order to come back to Earth from L1, we need to carry 13,000 kilograms of fuel with us, and we'll use that to get back to low Earth orbit. So the Nerva tug is around 20,000 kilograms, and the return fuel is 13,000 kilograms. We are going to assume that the tug can take around 50,000 kilograms of payload from Leo to L1. That's an assumption. Our total dry mass, so the sum of the above, the 50,000, the 20,000, the 13,000, is around 83,000 kilograms. The delta V is around 3,900. The exhaust velocity of the tug is 8,000 meters per second. So when we do all of the rocket equation stuff, we get 135,000 kilograms. So the fuel mass is around 52,000 kilograms. So in essence, we need 2 Falcon Heavy launches to get 1 container from Leo to the moon Earth L1 point. So for launch 1, we launch 50,000 kilograms of payload, just the payload, to L1. We launch a second time, we launch 52,000 kilograms of fuel for the tug, and then we combine those two things, and then we can actually launch the tug from Leo to L1. So for every 50,000 kilograms of payload that we want to go from Leo to L1, we need to have 2 launches of the Falcon Heavy. So we need to now count how many Falcon Heavy launches we need. So launch 1 and 2 would be, we're going to launch the lander and the fuel, and we're going to launch the Nerva tug. Launches 3 and 4, plus 5 and 6, are long-haul transporter. We need 100,000 kilograms for our long-haul transporter. So that requires 2 trips. So we're going to break our long-haul transporter into one 50,000 kilogram bit and another 50,000 kilogram bit. 2 launches for each of those 50,000 kilogram bits. So that's 4 launches total to get the long-haul transporter up to L1. Then we need to launch the fuel for our long-haul transporter. The launches are 7 plus 8, 9 plus 10, and 11 plus 12, and that gets us 150,000 kilograms of fuel at L1. So then we can complete our trip to Mars. Okay, so the summary of this idea is that we launch containers into Leo. We take a tug from Leo to the moon Earth L1 point. We assemble the ship at the Earth Moon L1 point. The ship assembly takes 12 Falcon Heavy launches, and each Falcon Heavy launch costs around $100 million roughly. So that's $1.2 billion. But that's, that's the cost of doing business in space. 12 Falcon Heavy launches. Like we said at the beginning of this, Falcon Heavy launches are relatively routine, and so they can be done pretty easily. We can scale our ship size with more Falcon Heavy launches. The concept is that we just assemble the ship at some place in space, at the moon Earth L1 point. Then Once it's fully assembled, we use our tug to push the ship through the home and transfer to Mars. Then we arrive at the Mars-Sun L1 point, and we use some sort of a lander combined with atmospheric braking. So we use thrusters and atmospheric braking to land on Mars. And that's the summary of this idea. So we can put 3,000 kilograms on Mars now using one big rocket like a Delta IV Heavy or even a Falcon Heavy, but we can't do more than that. If we want to put humans on Mars, it's going to require a much, much, much larger ship. And that is impossible to actually do this now because we can't even get 100,000 kilograms in low Earth orbit right now. So we're going to have to build it in space, like the International Space Station, which actually took 30 to 40 shuttle missions to fully assembled. We're going to do this by using tugs from Leo to the Moon Earth L1 point, when we're going to assemble all of our ship there. And then the general idea would be to use something like a Nerva engine to actually get us there because it has a very large exhaust velocity. But we could use a different technology like plasma engines. Plasma engines have a much higher exhaust velocity than even Nerva engines, but they can't provide very much thrust. So it would just take a huge amount of time to move them from different places. Once we assemble them, we use the tug from Earth to Mars through a home and transfer. We use the Nerva to do that, Nerva engine or some sort of similar technology to use that. And then once we're at the Mars-Sun L1 point, we use a lander to go to the surface. And this is very similar to what we have done at the moon in the past. In order to do this, we only need 12 Falcon Heavy launches, plus the development of a Nerva engine. And so it's a big ask. But if we want to put humans on Mars, this is about what we're going to actually have to do.